Okay, welcome back everyone. Today I'm going to be making a video on constraint optimization and Lagrange multipliers. Um, so again, Lagrange multipliers are essentially an optimization method given some kind of constraint. So it's a type of constraint optimization. And this just to rigorously define what constraint optimization is, it's essentially just getting the maximum of a given graph f of x, y, given a certain parameter. So in this case, I want you to consider the following graph, which I tried to draw, um, and I want you to try to visualize some kind of unit circle that's projected onto the graph. So I tried to draw like a wobbly unit circle on the graph. So essentially, the unit circles are constrained, and the equation for a unit circle is x squared plus y squared is 1. And our goal is essentially to find the maximum possible point, x naught, y naught, here, such that, but let's say x sub m, y sub m, such that this graph here is at a maximum point. So the value somewhere on this projected unit circle, such that the value f of x m, y m is at a maximum. So let's see how we might calculate that. And a good way, perhaps, to visualize something like this is to consider a contour plot. So we can imagine saying that, well, obviously our contour plot of our parameter x squared plus y squared equals 1 is just going to be a unit circle on the xy plane. And now we want to consider the contour plot here. So we can kind of focus on a certain part of the contour plot. So if we let our we get these values when we let our function xy equal some value, some constants, and that's where we get these values. And we want to maximize the c, right, such that we get a value here such that the contour f of xy equals c intersects with this unit circle. So an example of something that works here is like these two contours. It's not accurately drawn, but this is kind of an idea of what a contour here looks like. And you might have like stuff back here. I don't know. Yeah, but we can just focus on these parts. These are the important parts. So notice that obviously it intersects twice here, so that tells us that there are points that satisfy our parameter on this function f of x, y. So, but we want to find the maximum of this. So this might be at some value c1. So let's say this is at some value c1. But then we can have this graph here, which actually doesn't even intersect with the circle, and that would be at let's say that's at C2. And notice that C2 is greater than C1. Okay? So, but we want a value that's at its maximum, but it also intersects with this circle. And that would be if it were to intersect, if it were to exactly go tangent to our unit circle. So I'm going to redraw that. That would be the maximum possibility. So if I were to draw that, well, we would just have the following. So we could just focus on this side, right? It goes exactly tangent at the desired point. Okay, so now let's think about how we would compute this. Okay, so let's say this is some point xm, ym, like I said earlier. Now, we want to find something that's in common with these points. So notice that their tangent vector, well, the tangent vector is going to be, their tangent vectors are going to be scalar multiples of each other at this point. So let's say this is the tangent vector to this contour, but then this is the tangent vector to this contour. Okay? So notice that Well, we have a very nice property, and that property is that the gradient of a function, the gradient of a multivariable function is always at some point xm, ym is going to be normal. It's going to be normal to the graph, the contour, at some point, right? And to prove that, well, let's look at any old multivariable function here. And then if we look at some contour, let's say we get some kind of plane thing here, right? And then we consider some path along here. And let's let the tangent vector here be like v, right? It's going to be r prime. So some vector r prime equals v. Okay, and so this is at some f of x, y equals some constant c. So now I want to quickly use the multivariable chain rule. And that tells us that I'll let this, we can write, or I'll just write it as df dt, which, well, it's defined to be 0 along this contour. So it's 0, which is equal to, by the multivariable chain rule, it's going to be equal to the partial derivative of f with respect to x dx dt plus the partial derivative of f with respect to y dy dt. Okay, but notice that this is the same thing as the dot product of the gradient of f and r prime. So we're letting r of t be like x of t, y of t. Okay. Well, notice that by definition, by the geometric representation of what a dot product is since the dot product of these two is 0, they're perpendicular. That's exactly what we wanted to show. It's perpendicular to any point along this path, and thus anywhere in this contour, right? Okay, so now let's use this fact here. So this tells us since they have the same tangent, they have the same, their tangents are scalar multiples of each other, since they're literally tangent at this point xm, ym. Then that implies that at this point their normals are also they're in, well, by the fact that we proved here, their normals are also going to be scalar multiples of each other, but that tells us that their gradient vectors are going to be multiples of each other. Since they're going to be perpendicular, they're going to go in the same direction, but their magnitudes are different. That's another way of putting it. So, well, I'm going to let this general function be g of xy, and this general function be, this is already f of xy, and this is just to generalize it. So generally we'll have g of xy, normally you might call this like the budget in a real world analysis. So we can let this be some constant, let's say b. Okay, and in general, what we have, and this is where Lagrange multiplier comes into play, it's that the gradient of f of xy we should say at this point, the maximum xy, xm, ym, it's going to be equal to lambda, and this is the Lagrange multiplier. This is what the whole talk is about. Essentially, multiplied by the gradient of g of x, y. And, well, notice that this is an equation, but it's at some contour, so we're not worried about this equal sign. We're essentially, yeah, we're letting some multivariable function equal a constant, which is a contour at that level. Okay, so again, this is the idea. Oh, I should have said xm, ym. Okay. So, yeah, so that's the general idea, and we can start working that out for our example here. F of xy equals x squared y, and g of xy is equal to 1. So let's try that out real quick. So what's the gradient of f of xm, ym? Well, let's see. So we're going to have the gradient here. And for now, we'll just replace these with x and y, and we're going to solve for x, y. It's just going to be a way to write a bit less. So let's write the gradient of f. The gradient of f is going to be 2xy, so the partial derivative of this with respect to x. And then we have x squared to be equal to lambda as gradient of this, so that's going to be 2 lambda x, then 2 lambda y. Okay, so we have this. Now we can set these things equal to each other. Oh yeah, and our final constraint is going to be this third equation. So we have all three of these equations to work with. So we're going to have x. So now, for now, let's suppose x is not 0, and we'll deal with that case later. But if x is non-zero, then if we take 2xy equals 2 lambda xy, we can divide both sides by 2x. So we're going to get y equals lambda. Yep, y equals lambda. Okay, but then that tells us that, let's see, yes, I'll write this like this. So this tells us that y equals lambda. Okay, but then let's try this equation. So that tells us that x squared is equal to 2 lambda times y, which is lambda. So it's 2 lambda squared. So that tells us that x is equal to, well, technically we don't really need to solve for x. We don't even need to solve for x because we already have this constraint here, x squared plus y squared equals 1. So let's just use that. So let's just directly plug it in to solve for lambda. So we have 2 lambda squared, and then y equals lambda, so plus lambda squared is equal to 1. Then that just tells us that, well, just check our work. Yep, that's correct. So we're going to have lambda equals plus or minus 1 over the square root of 3, right? Because this turns into 3 lambda squared equals 1. Divide both sides by 3, and then take the square root. Yeah, and this is what we end up with. Or if you want to rationalize, we have square root of 3 over 3. Okay, and then now you can essentially just plug into the points and see what the values output. So I guess we can do that fairly quickly here. Well, y equals lambda, so y is going to equal plus or minus square root of 3 over 3. And, well, x is equal to, x is just equal to, or I guess I should, I guess I have to solve for x in this case, which is a bit tedious, but it tells us that x is equal to plus or minus the square root of, I guess I could put it like this, so the square root of 2 lambda, okay? And then lambda is plus or minus that, so we're just going to get, in general, plus or minus the square root of 6 over 3. It looks like that's the case, right? Okay, so that gives us our values for x. And if x equals 0, well, let's see. If x is 0, then that tells us that 0 equals 2 lambda y, which tells us that y is equal to 0. Okay, so let's see. But notice that these two values will not satisfy this third condition, because if x and y grow 0, 0 is not equal to 1, right? So that essentially, oh yeah, and you can try to actually check these solutions, and they will end up working. Okay, so that is it for this video. I hope you enjoyed, and have a nice day. Goodbye. Oh, and I might make a part 2 to this, so have a nice day.